In this video, I'll introduce inductors, which are our second type of electrical energy storage element. Inductor models are very similar to the ones we used for capacitors, except that the roles of current and voltage are reversed. Capacitors store energy as an electric field between two conductive plates. Inductors store energy as a magnetic field. Physically, inductors can be created by winding a conductive wire around some core. When current flows through the wire, a magnetic field is created. This magnetic field stores energy. This is the circuit symbol for an inductor. Inductors are passive circuit elements, so we have to follow the passive sign convention when assigning our inductor voltage and current. The inductance of the inductor is represented as L. Inductance has units of henries, which is abbreviated by a capital letter H. The inductance indicates how much energy is stored in the inductor for a given current. For a given current, a higher inductance results in more energy storage. The IV characteristic for an inductor is that voltage is equal to the inductance times the derivative of current with respect to time. An alternate formulation can be obtained by integrating both sides of this equation, so that the inductor current is 1 over L times the integral of the voltage plus an integration constant that corresponds to the initial current through the inductor. The inductor current dictates the energy stored in the inductor, since energy is always the result of an integration. As an example of this, let's look at the voltage corresponding from applying this current waveform to an inductor. The voltage is the rate of change of the current, so in this time range, the voltage will be a positive constant. While the current is constant, the voltage will be 0 since the current change with respect to time is equal to 0. Finally, in this range of time, the voltage is a negative constant corresponding to the slope of this line. Notice that the voltage can change instantaneously, but the current cannot. Next, let's look at the current resulting from applying this voltage waveform to an inductor. The current is the integral of the voltage. So in this time range, the current will increase at a constant rate, since the area under the voltage waveform is increasing linearly. While the voltage is 0, the current remains constant, since the current change with time is equal to 0. Finally, in this range of time, the area under the voltage curve is negative, so the rate of change of the current is a negative constant. Next, I'll look at some important special cases relative to the inductor voltage-current relationship. First, if the current is constant, the voltage difference across the inductor has to be 0, since voltage is proportional to the time rate of change of the current. This means that if the inductor current is constant, the inductor behaves like a short circuit, which also has 0 voltage difference. An inductor's current will become constant anytime a constant input, either a voltage or a current, is applied to the inductor for a long time. As with capacitors, this property helps us determine the particular solution of differential equations with constant forcing functions, which I'll talk about in more detail later. In order to change the current instantly in an inductor, the voltage would have to go to infinity. Since there's no such thing as an infinite voltage source, that would require infinite power, we can't change an inductor's current instantly. This property will help us find initial conditions on the differential equations we'll write and solve later. Now let's do an example of these properties of inductors. In this circuit, the switch is at position A before t equals 0. At t equals 0, the switch instantaneously moves from position A to position B. We want to find the inductor current, I, just before the switch moves at t equals 0 minus, just after the switch moves at time t equals 0 plus, and as t goes to infinity. At t equals 0 minus, the input is constant, and it's been constant for a long time. That means that at t equals 0 minus, the inductor looks like a short circuit and there's no voltage difference across the inductor. So the circuit becomes a 6-volt source, this 2 ohm resistor, a 4 ohm resistor, and then this inductor that looks like a short circuit. The current through this short circuit is I at 0 minus. Since this has no voltage difference, no current goes through this resistor, and the current through the inductor is just 6 volts over 2 ohms, which is 3 amps. The transition of the switch from point A to point B happens instantaneously, but the inductor can't change its current instantaneously. So the current at t equals 0 plus is the same as the current at t equals 0 minus. After the switch moves, the inductor is again connected to a constant input. If I wait for a long time, the inductor again looks like a short circuit. This inductor becomes a short circuit. It's now connected with a 1 ohm resistor, a 2 ohm resistor, and this 3 amp current source. We want to find I at infinity. These two resistors are now in parallel. I at infinity can be found from a current divider. So I of infinity is equal to the total current, 3 amps, times the other resistance, 2 ohms, over the sum of the two resistances, 2 ohms plus 1 ohm. That's 2/3 of 3 amps, so I at infinity is equal to 2 amps. The voltage at t equals 0 plus is the initial condition on the differential equation that models the inductor voltage for t greater than 0. The process of the transition from its initial to its final value requires us to solve that differential equation, which we'll do later. Finally, I'll show why the inductor current dictates the energy stored by the inductor. Power is the product of voltage and current. Since the inductor voltage is equal to L times di by dt, the power is I times L di dt. By definition, energy is the time integral of power. If we integrate this expression, we find that energy is equal to 1/2 L times the square of the current evaluated at the limits of integration. If we assume that the inductor current is 0 at t equals negative infinity, this means the energy at any time is just 1/2 of L times the square of the current at that time. So if you tell me the inductor's current, I can tell you how much energy is stored by the inductor. The current uniquely defines the inductor energy. This is important, since if we know the inductor energy, we can find out anything else we need to know about a circuit that contains that inductor. Circuits containing energy storage elements are governed by differential equations. The order of the differential equation describing the circuit is equal to the number of independent energy storage elements in the circuit. Capacitors or inductors, when placed in series or parallel, are not independent. Later, I'll talk about combining capacitors and inductors.